welcome back to our magic tutorials for chemistry. We'll discuss Werner's theory for coordination compounds. So Alfred Werner, he was the first person to explain about the coordination compounds. So the postulates of his theory, that is the central metal atom, we also write it as CMA, the central metal atom, it exhibits two types of valencies. The central metal atom exhibits two types of valencies. Okay, so what type of valencies? That is primary and secondary valency. One is primary, one is secondary, right? So let's see what it is. Primary valency, it represents the primary valency, it represents the oxidation number of the metal. It represents the oxidation number of the metal. That is the central metal atom. Correct. For example, if we take the complex COCl3. Correct. So the oxidation number of the metal here, the metal is cobalt here. If we find the oxidation state, X plus 3 chlorine minus 1 equal to 0. So the oxidation state of the metal, it is plus 3. Correct. So for this compound, the primary valency is plus 3. Next point is the primary valency, it is ionizable. The primary valency, I am writing 1 degree, that is primary. It is ionizable. Correct? Why it is ionizable? Because it is always written outside the square bracket. It is written outside the square bracket. It is written outside the square bracket. Correct? So any complex, we will take any compound. Suppose if it is written Cl2 outside the square bracket. Right? Cl2 is outside the square bracket. That means the counterion, this is the counterion, Cl2 is the counterion. So it is ionizable. Means when you dissolve this in any solvent, it splits into two. The complex will remain as it is, that is a square bracket will remain as it is, and Cl will form 2 Cl minus ions. And the complex remains as it is. Correct? So that part, it is ionizable, the counterion, which is written outside the square bracket. Next it is, they are non-directional. That means outside the square bracket only the primary valency is written, that is a counterion. Right. So it can be written or it can be in any direction. Non-directional, it can be in any direction. So if it is in any direction, that means it will not give geometry to the complex. Somewhere we are drawing, correct, around this complex. That means it will not give any geometry to the complex. So primary valency do not give geometry to the complex. So these are the postulates for Werner's theory for coordination compounds. This is the first postulate for primary valency. We have already written the central metal atom exhibits two types of valency. So primary valency means the counter ion, which is written outside the square bracket. We will move to the next secondary valency. 2 degree, that is secondary valency. So let's check what are the points for secondary valency. So secondary valency represents, the first point is secondary valency means it represents the coordination number of the metal. It represents the coordination number of the metal. That means the central metal atom. Secondary valency, it is non-ionizable. It cannot be ionized. Third point is, it is written inside the square bracket. See, just the points opposite to primary valency we are writing. Written inside the square bracket. Inside the square bracket. And it is directional also. It is directional. That means if it is directional, means it is arranged in a proper way, correct, towards the central metal atom. So it will give geometry to the complex. Secondary valencies, they give geometry to the complex or to the coordination compound. Correct. So let's take one example. It is written inside the square bracket. That means it is with the central metal atom inside the square bracket. So let's take one example here. CO, NH3, 6 and Cl3. Correct. So what is the primary valency here? What is the secondary valency here? So what is written outside the square bracket? That is primary valency, that is Cl. It is a primary valency. What is written inside the square bracket with the central metal atom? Central metal atom is cobalt here. So what is written along with that? The ligand. Correct. That is the secondary valency. Correct. So secondary valency NH36, that is a secondary valency. It represents the coordination number of the metal. Okay, coordination number, that means how many ligands are attached to the central metal atom. So the coordination number for this metal, it is 6. Correct. Secondary valency means it represents a coordination number. What do you mean by coordination number? How many ligands are attached, and here you have to consider the donor site also. Each ligand, how many donor sites? Here I taken the example of NH3, it has one donor site. Correct. So total how many are there? 6. So the coordination number or the secondary valency, it is 6. It is non-ionizable because it is inside the square bracket. It cannot be split. The metal and the ligands cannot be split. Correct. Counter ion can be split. It is written inside the square bracket. It is directional also. They are the ligands, right? The ligands has to be arranged in a particular certain way around the central metal atom. So if it is arranged in a proper way, that means it gives geometry to the complex. It gives shape to the complex. So hope these are the two postulates regarding the primary valency and the secondary valency. Hope this is clear to you. So Werner added cobalt 3 complexes with an excess of silver nitrate solution. Okay, he added cobalt 3 complexes, 3 plus complexes with excess of silver nitrate solution. Correct. So let's check what it will form. So COCl3, this was the complex that he took. Correct. COCl3 attached with the 6NH3. This was the complex he has taken. He added to this excess of AgNO3. I'll just write it as excess of Ag plus. Correct. So So at that time the product formed was AgCl and 3 moles of AgCl was produced. That means 3 Cl minus ions were precipitated. See, I am giving examples for what I have written here. Cobalt 3 plus complex he took. Okay, this is the complex. Into this he added excess of AgNO3 solution. So what product he got? What was the precipitate? 3 AgCl, 3 moles of AgCl, right? That means 3 Cl minus ions were precipitated. Next complex, he took COCl3, again the cobalt complex, and this was 5NH3, correct? Again he added excess of Ag plus, same thing, right? Excess of Ag plus. At that time 2 moles of AgCl was precipitated. That means 2 Cl minus precipitated. 2 chloride ions were precipitated. Next he took cobalt complex COCl3, 4NH3. Correct? Again he added excess of Ag plus. At that time 1 mole of AgCl was precipitated. That means out of this, same I am writing here, 1 Cl minus precipitated. Correct? Next he took cobalt complex, that is COCl3, 3NH3. Excess of Ag plus. At that time no PPT was formed. No PPT. That means we can write 0 chloride ions were precipitated. So this was the observation. He took cobalt 3 plus complexes. You can calculate the oxidation state of cobalt here. It will be 3 plus. Why? Because ammonia NH3 amine, that is a neutral ligand, charge is 0. Correct? So if you find the oxidation state of CO cobalt here, it is plus 3. So he took this complex, into that excess of AgNO3 solution was added. So what was the precipitation formed? AgCl. You can see here more NH3 we are taking, 3 AgCl. 5 NH3 less NH3, 2 AgCl. 4 NH3, 1 AgCl. 3 NH3, no PPT, no precipitate at all, right? So from this he wrote new formulas for the compounds. He wrote new formulas for the compounds that we will check now. You can copy down this so that you understand. In the first one 3 Cl minus, second one 2 Cl minus, third one 1 Cl minus, and the last no Cl minus were precipitated. Yes, so in the first case 3 AgCl, that is 3 chloride ions were precipitated, right. So what was the formula that we wrote? COCl3 and 6NH3, right. So COCl3, 6NH3, that was the first cobalt complex he took. At that time 3 AgCl was precipitated, right. 3 chloride ions were precipitated. So how we will write this is, whatever the amount of chloride ions are precipitated, number of chloride ions precipitated, that we will write outside the square bracket. Okay. So here 3 chloride ions, in the first case 3 chloride ions were precipitated, right. So how we will write the formula for the complex? It will be CO, correct, square bracket CO, write the NH3, 6, precipitated, that means it is ionized, precipitated. So we will write it outside, correct, we will write it outside. How many precipitated? 3. So write Cl3, correct. So this was the formula for the coordination compound. That was for the first one. For the second one, what was the complex taken? COCl3, 5NH3, right? At that time 2 AgCl, that means 2 chloride ions were precipitated. So 2 chloride ions should be outside the square bracket. So I will write it as Cl2. Now what is left here? Cobalt, right? NH3 5, the ligand. Cl2, 2 Cl I have written outside. So how many Cl should I write inside? Only 1 Cl. So this Cl, it is also acting as a ligand, which is inside the square bracket, that will be the ligand. Outside the square bracket, that is a counterion. The next complex, COCl3 4NH3. When this complex was taken with excess of AgNO3, 1 AgCl, that means 1 chloride ion was precipitated. So the formula will be 1 chloride ion, you have to take it outside the square bracket, correct? So inside the square bracket, it will be CO NH3 4 Cl2, correct? Total Cl 3. 1 chloride ion precipitated, that will go outside the square bracket. The last complex what he took is COCl3, correct? 3NH3. So at that time 0 chloride ions were precipitated. So we will just write the complex as it is, CO ligands NH3 whole thrice, Cl3 let it be inside, because there is no precipitate, right? Whatever precipitated, that ions will come outside as the counter ions. So 1, 2, 3, 4 what I have written, they were the new formulas for the coordination compounds as found by Werner. So from these formulas, first, second, third and fourth, these formulas he concluded that the chloride ions, okay, what did he conclude is the chloride ions which are written outside the square bracket. Chloride ions, here no chloride ions, correct? So the chloride ions which are written outside the square bracket, they are the primary valency and NH3, correct? Here NH3 and Cl, here also 4NH3 and 2Cl, here NH3 3 and Cl3. Whatever I have underlined, they act as a secondary valency. So the counter ion will act as the primary valency and the ligands will act as a secondary valency. So he represented the primary valencies by dotted lines and secondary valencies by a solid line, means just a straight line. Okay. So this was the first complex, correct, according to the formula. So how to draw this? CO, how many ligands are there? 6 ligands inside, right? With the CO, how many are attached? 6 NH3. So that is a ligand here. So ligands, we will show it with the solid lines, correct? 6 ligands, that means it is octahedral. So 1, 2, 3, 4, 5 and 6. Everywhere I will write it as NH3. NH3, correct? 6 ligands I have arranged here. I have shown it with the solid line because that is a secondary valency, correct? This is the secondary valency. This is the primary valency, secondary valency with solid lines, right? So I have shown the ligands here. Now secondary valency, how I have shown here. Now the primary valency, correct? Primary with the dotted lines. So 3 are there, we will just arrange it, dotted lines, correct? Cl, again here the dotted lines, Cl, here the dotted lines, Cl. Correct? Right? So this depends upon the depression in freezing point, correct? Depression in freezing point. So greater the number of particles, greater the number of particles, compounds will be given to you, you have to arrange them. Okay. So, greater the number of particles, more will be the freezing point. So, cryoscopic measurement means it depends on the depression in the freezing point. So, greater the number of particles, more will be the freezing point. So, check for the counter ions always. Counter ions and the entire entity, the complex, which is written in the square bracket. Correct? So, more the number of particles, more will be the freezing point. The second one, that is electrical conductance. Electrical conductance. Again, greater the number of particles, if the number of particles are more will be the conductance. Greater the number of particles, if many particles are there, then all the particles will start conducting, right? So, more will be the conductance. The next one is precipitation. So, precipitation, greater the number of counter ions, PPT increases. Greater the number of counter ions, greater the number of counter ions means which is written outside the square bracket. Okay. Precipitate formation, that is PPT formation, increases. So, let us discuss with how many cations, how many anions, total ions, and what is the charge on the complex ion for each of the complex. So, the first complex is CO, NH36Cl3. How many cations are there? The entire entity you take, 1. Correct? Entire square bracket entity, that is 1. Anion means the negative ions present outside the square bracket, that is 3. Correct? Cl3, 3. So, total ions 3 plus 1, 4. What is the charge on the complex ion? So, see for the anion here 3 are there, right? So, the charge on the complex will be 3. Write it as plus 3. Correct? The second complex it is CO, NH3, 5, Cl and Cl2. So, how many cations are there here? 1 cation. The entire entity you consider it as cation 1. How many anions are there? Negative ions 2. So, total 3. Correct. Charge on the complex ion will be how many? 2. So, plus 2. Third complex, CO, NH3, correct, 4, Cl2, Cl. So, how many cations are there? The entire entity 1. How many anions are there? 1 again. Anion means what is written outside the square bracket. Total 2, right? And charge, how many are there? Only 1. So, charge is plus 1. The last complex, CO, NH3, 3, yeah, it is inside, that is Cl3, right? Cl3. So, how many cation? The entire entity is a cation. So, that is 1, right? How many anions here? 0, correct? No anions are there. So, it is 0, correct? So, total 1, total number of ions is 1, right? So, what is the charge over here? That is also neutral. So, limitations of Werner's theory. The first limitation, it did not explain about the color of the complex, whether the complex is colored or it is colorless. Second, it did not explain the magnetic properties and optical properties. Third one, why the complex possesses a definite geometry. Correct. We have drawn like cobalt, it is attached to the ligands. Correct. The primary valency, it is shown by dotted lines. Secondary valencies with a solid line. Correct. We just drew it, but it did not explain about the geometry, how it is arranged. Correct. So these were the limitations. So here we complete with Werner's theory for coordination compounds. Hope it is clear to you. Thanks for watching.